study that how we can calculate the gain margin and phase margin from polar plots of a system. So, to know that how we can calculate the gain margin and phase margin, first let us understand that what is a gain margin and what is a phase margin. First, we will study the gain margin. Gain margin, it is denoted also known as GM, and it is defined as so gain margin is defined as the factor by which the system gain can be increased to drive the system to the verge of instability. That is, it is the amount by which we have to increase the system gain so that the system it goes towards the instability area. Okay. Now the gain margin, how we can get it from the polar plot. So the polar plot of a system, it crosses the negative real axis at omega equals to omega p. At this frequency omega p, it is called the phase crossover frequency. P is for the phase and it is known as phase crossover frequency, and at this frequency whatever will be the magnitude, that is G J omega P H J omega P, that is magnitude at omega equals to omega P, it is denoted as M, and this M is less than 1. If we see on the polar plot, it will be like this is the polar plot, imaginary axis, real axis, and this is the polar plot. Now, if we have a unit circle here, then this is 1, that is minus 1 plus j0, okay, and this is less than, this is polar plot and it is crossing the negative real axis at the frequency omega equals to omega p. Omega p is called the phase crossover frequency. And at this frequency, this is the magnitude and it is m. So this m, it is less than 1. Okay. So if the gain k of the system So if the gain k of the system it is increased so that the plot it crosses the point -1 plus j0. Why this point -1 plus j0 is taken at the stability point? Because let us first understand this. We have on the, if we want to define the stability, then what we say that the poles of the system it should lie on the left hand side of the j omega axis. Okay, left hand side of the s plane. This is our j omega axis, this is sigma, because s plane is what? Sigma plus j omega. So on the left hand side, if the poles are lying, then the system is stable. Now, if we define this and the unit circle, when we convert it, this imaginary axis to the unit circle, then what we are having, this real part will be 0, and we have the stability condition, that is 1 plus GSHS equals to 0. So GSHS will be equals to -1. If we take its magnitude and express this complex plane, that is sigma equals to j omega. J omega, it is the imaginary axis. So this imaginary axis, when we convert it, it becomes a unit circle, which is -1 plus j0. This is the point on the real axis, and this is -1, and this imaginary axis has been converted into a unit circle. So if any of the point, if the roots are lying outside this unit circle, then the system is unstable, and if the roots they are lying inside this unit circle, then the system is stable. Okay, so now here when the magnitude it is less than 1, then the system is unstable, and if we increase the gain k of the system, then the plot it will cross the -1 plus j0, and it will go outside this. Inside the system is stable because it is having all the roots inside this unit circle. Now if the gain k is increased, it will, the plot will move outside, and the system will start moving towards instability. So what we have defined the gain margin. Gain margin was the factor by which the system gain has to be increased to drive the system towards the verge of instability. Okay, so we are increasing the gain k so that this plot it crosses the -1 plus j0 point, so that the system goes to the instability area. Okay, so the magnitude m, this magnitude m, so the magnitude when this polar plot it is going to cross this point, then the magnitude will be equals to 1. So the magnitude of m is equal to 1 at this point. Okay, so gain margin, it is what? It is the amount by which we are increasing this gain so that the system goes to the verge of instability. So if we write the formula for the gain margin, then gain margin we calculate it in dBs, that is decibels. Its unit is decibel, and it is given by 20 log to the base 10 1 upon the magnitude. So magnitude is what? G j omega p h j omega p, and it is in dBs. Okay, so it is the formula for the gain margin. It is what? 20 log 10 1 upon m, because m is this magnitude. Okay, another formula will be -20 log to the base 10 m. If we convert it and take its reciprocal, then we will introduce here minus sign. So gain margin, that is GM, it is equals to minus 20 log to the base 10 M, that is magnitude. So we can say that the gain margin, it is also defined as reciprocal of the magnitude of the open loop transfer function. Here open loop transfer function is this GS and HS at the phase crossover frequency. It is saying that it is the reciprocal of the magnitude of the open loop transfer function at the phase crossover frequency. That is GM is equals to 1 upon Gj omega Hj omega at omega equals to omega p. That is the phase crossover frequency. Now, if we see that how we can calculate it from the that polar plot, then let's see the polar plot of a system. This is imaginary axis, real axis, and it is the polar plot of a system. Now we are having a unit circle here. Now this unit circle, it is having the radius as 1. So this point will be minus 1 plus J0. J0 because it is lying on the real axis, so imaginary part will be 0 and only the magnitude minus 1 will be there. It is minus 1, this is plus 1. This is imaginary part, so it will be J and this is minus J. Okay, real part will be 0 here. So this point will be minus 1 plus J0 if we denote it in complex form. Now, this polar plot, it is crossing the negative real axis because this is positive real axis, this is negative real axis. So this polar plot, it is crossing the negative real axis at a frequency omega equals to omega p, and omega p is what? Phase crossover frequency. Now at phase crossover frequency, whatever will be the magnitude, this magnitude that it is given by m equals to magnitude at the phase crossover frequency. Okay, this is value will be m. At this magnitude m, it is the gain. This magnitude we have calculated, and the gain margin will be reciprocal of this magnitude, that is 1 by m. So we are having here positive gain margin. Okay, positive gain margin because the system is stable until and unless the polar plot is inside this minus 1 plus J0 or inside this unit circle. So this system is stable. If this polar plot, it crosses this minus 1 plus J0 point, then the system becomes unstable. So we can say that for a stable system, the gain margin should be positive and the magnitude m, it is less than 1 here. So m should be less than 1. If these two conditions are found, then the system is said to be stable. Now, if we calculate the phase crossover frequency, if we want to calculate that what is the phase crossover frequency, we take the phase of the transfer function as equal to 180 degree. Okay, so because on this graph you can see on this polar plot that when this polar plot it is touching this, intersecting this negative real axis, then the angle is 180 degree. That is on phase crossover frequency, the phase angle is what? 180 degrees. So you have to just put the phase angle in the transfer function as 180 degree, then you will be able to find out the phase crossover frequency. So phi, that is angle of G J omega P H J omega P is equals to 180 degrees, or we can say pi radians. Okay. Now the polar plot which we have seen, that is for the stable system. Now for unstable system, what will be the polar plot? This is the unit circle, and the polar plot, it is going to cross this point -1 plus j0. Okay, when this is crossing this, that means that it is moving from stability to the unstable condition, because inside the unit circle the system is stable, outside it is unstable. So when it is crossing this point, it is marginally stable. When this polar plot, it is crossing this point, and m, it is less than 1 inside this, here m will be equals to 1, magnitude is equals to 1. An unstable system, this is the unit circle, and the polar plot, it is going outside this unit circle. This is the point -1 plus j0. We are having here negative gain margin, and our magnitude, it is greater than 1. Inside, magnitude is less than 1. Inside this, the magnitude is less than 1 and the gain margin is positive. At this point, the magnitude is equals to 1 and gain margin is equals to 0. And outside this, the gain margin is negative and the magnitude is greater than 1. So if the polar plot, it is going outside this unit circle, then the system is unstable. Okay. So this is how we can say about the stability of the system through the polar plots, and what will be the value of the gain margin and the magnitude when the system is unstable or stable. So let's summarize these points. First, we have that if the polar plot intersects the negative real axis between the origin and -1 plus j0, then magnitude is less than 1, gain margin is positive, and system is stable. And also, more the gain margin, more positive the gain margin is, more stable is the system. So if the polar plot, it is intersecting the negative real axis, let's draw the polar plot for this. This is unit circle and polar plot is intersecting the negative real axis between the origin and the -1 plus j0 point. This is origin. So if the polar plot is like this, then the system is stable. M, that is G J omega P H j omega P, it is less than 1, and gain margin, that is reciprocal of this gain margin in dBs, it is positive. Next we have, if the polar plot encloses the point -1 plus j0, then magnitude is greater than 1, gain margin is negative, and system is unstable. That means the polar plot will be like, this is the unit circle and this plot is intersecting outside this unit circle, that is -1 plus j0. M will be greater than 1, gain margin will be negative, and the system is unstable. Then we have, if the plot intersects the negative real axis at -1 plus j0, then so if the plot it is intersecting the negative real axis at this point -1 plus j0, then the system is marginally stable. This is the point -1 plus j0. At this point, m will be equals to 1 and gain margin will be equals to 0. So the system is marginally stable because it is shifting from the stability condition to the instability condition. Now, if the plot it does not intersects the negative real axis, suppose we are having a plot which is not intersecting the negative real axis, then magnitude is equals to 0 and the gain margin it is infinity. So these are the four conditions: when the gain margin is positive, when gain margin is negative, when gain margin is 0, and gain margin is infinity. So these are the four conditions depending upon which we can define the stability of the system. So this was all about the gain margin. Now how we can calculate the phase margin from the polar plots? Let us see. First let us define that what is a phase margin. Phase margin, it is defined as the So phase margin is defined as the additional phase lag that can be introduced before the system becomes unstable. So this is the amount which we can add in the phase so that the system does not becomes unstable. If we see on the polar plot, this is again the unit circle and it is the polar plot. Now this polar plot, it is intersecting this unit circle at this point. So this is the frequency, that is gain crossover frequency. And the angle which this point it is making with this negative real axis, it is called the phase margin phi p in. Okay, this is a point 0, this is A. So let us take a point A, which is the intersection of this polar plot and the unit circle, and this unit circle is centered at the origin. This is origin O point, and we are joining these O and A points, and then we are measuring this phase angle. So this phase angle is the phase margin. Here we are having positive phase margin, and this is the point -1 plus J0. So how we can obtain the phase margin? We are having a point A, which is the intersection of this polar plot with the unit circle, and we are joining these points O and A having this R, and then measuring the angle made by this line OA with the negative real axis. So this angle will be the phase margin. So phase angle between line OA and negative real axis is the phase angle at the gain crossover frequency. So this phase angle which we have obtained, it is the phase angle at the gain crossover frequency, and this gain crossover frequency is denoted by omega g, and we can write it as phase angle gj omega hj omega. It is the phase angle at the gain crossover frequency, that is at omega equals to omega g. Now if an additional phase lag of phi pm, that is the phase margin, is introduced at this frequency, then the phase angle at the gain crossover frequency, it will become 180 degrees. You can see in the plot in the figure that this is the phase margin. If we add some phase in this angle 5 pm, that is phase margin, then this angle will be equals to 180 degree. It will become 180 degree. So this additional angle which we are adding to make the angle 180 degree, it is called the phase margin. It will be introduced at this frequency, then the phase angle will become 180 degree, and the point A coincides with -1 plus J0, and it will drive the system, driving the system to the verge of instability. Okay, so if we add this phase into this angle, then the phase margin, then the angle it is going to become 180 degree, and the system will go towards the verge of instability. So this additional phase angle which we are adding to make the phase angle 180 degree is called the phase margin. How we can calculate the phase margin? This is 5 pm and it is given by 180 degrees plus the phase angle at the gain crossover frequency. So this is the phase angle at the gain crossover frequency. We will add it to 180 degree. Then we are going to get the phase margin, because phase margin is what? 180. This angle will be 180 degree minus the phase margin. Okay. Now since this phi g, that is the phase angle at the gain crossover frequency, is measured in clockwise direction, it is taken as negative. It is taken as negative. Because whenever we measure the phase angles, then a positive phase angle, it is measured in anti-clockwise direction in polar plots, and the negative phase angle, it is measured in clockwise direction. So here we are measuring the phase angle at the gain crossover frequency in the clockwise direction, so we have to take it as negative. Okay, it means that this 5 p.m. it is the angle between the negative real axis and the radius vector joining the origin and the gain crossover frequency omega g. You have seen that in the figure we have joined the origin and the gain crossover frequency. This is the radius vector OA. So OA and the negative real axis, the angle between these two, it is the phase margin. So for stable system, the phase margin is positive. Okay, and for unstable system, the phase margin will be negative. Okay, so the phase margin, we have studied that it is the additional phase lag, so that the system goes to the verge of instability, unstable become. So it is given by this formula, we can calculate it. So in this video we have studied that how we can calculate the gain margin and the phase margin from the polar plots. Gain margin is what? It is 20 log log to the base 10 m. M is the magnitude. So it is the gain. It is the amount by which we have to increase the gain so that the system goes to the verge of instability. And phase margin, it is the additional phase lag so that the system goes to the verge of instability. So I hope this video is clear to you. Thank you.